Today we are covering logs and exponential functions where we're going to be converting between these two forms. So the first one just says rewrite each equation in exponential form. So you'll notice that all four of these have a logarithm written in it. So I'll do the ones on the left using what I called the swoop method, and then the other two will do the writing of the same base logarithm. Okay, or not logarithm, but the rule or the property. So at any point in time, please just try and practice and pause the video for yourself. All right, so with the logarithm form, when we go into the exponential, so writing just your standard one like this, they tend to have a very similar format. So your swoop method, we start on your base, we're going to come up and around and land on your x value. Now, by doing so, it kind of gives us the order in which to write these values. So going from a log to an exponential, we always start with your base b. So this is the first thing that we're going to write, b. Then notice that we came up and around y. So that'll be your exponent here, the next the one. And then your last one, you can say equals x is the very last thing. Some students like to do, I think it was called like the triangle method. I can't quite remember. That's something that I'm not super familiar with, but it has been in the past. So if we're replicating that, we're starting on your base of number 1, which locate your base. Should be 11. So we're going to come up and around and land on 121. Now, if you encounter a problem where you have the equal sign on the other side, you're just going to swoop to the other side, or you can just rewrite your expression to have the equal sign on the side that you would like. So this allows us to write your base first. So we have your base 11. We came up and around your 2. So now that's your exponent is equal to 121. And this is a true statement. 11 squared, or 11 raised to the second power, is 121. Let's try that again. So we start on your base 7, come up and around and land on 49. So then we write 7 squared is equal to 49. So if you're a fan of the swoop method, then that would be great for you. What my other method using the properties will do here. So one of your properties that you have to be aware of is if you have a log of one particular base and you have an exponential raised to another base, let's just say, oh, actually I wrote it the wrong way. No. So let's say we have an exponential raised to a logarithm with an equal base. So what this allows us to do, because they're equal in your bases, they are the same value, they're going to cancel, and it allows this value to drop. So think about it as kind of being the square root of x squared, which they undo the process of one another. That's what the inverses are. They kind of undo what one of them has done, and you're left with x. So for an example, if we took the square root of 2 squared, right? Well, the way it's written, we might want to do the square of 2. So 2 squared, or 2 times 2 is 4, and then take the square root of 4, which is 2. So one squared it and the other square rooted it. So they kind of cancel each other out, and you're left with what you started, 2. Same idea here and again here. One is doing the action and the other one is reversing it. So with that in mind, right, notice that we have a logarithm 9, and it's not written in this form where we have a base with a similar base. So that is up to us to use this property. So finding your base on example 2, which is 9, we can write the base of an equal measure on one side, and what you do to one side, you also have to do to the other. Now that your bases match, which they match as the 9 and the 9, they can go ahead and cancel and allow this 81 to drop. So 81 is equal to 9 squared, which again is a true statement. Doing it here, again, finding your base, 216. What you do to one side, you do to the other, 216. So the bases cancel and your 6 drops. So 6 is equal to 216 to the 1/3. Now, the reason why this is still a true statement, even though it looks unusual, is that this is actually a fractional exponent, which would be written as the cubed root of 216. So this can be written as 1 over, okay, to the 1 over b. Well, let's redo that. We'll just use x to the 1 over a. So by writing your a out front of your radical, let me rewrite that a so it doesn't look like a 9. We got your a outside the radical and the x on the inside with that same degree. If you wanted to, if you had more substance to your what is this called, a fraction, then whatever is on the denominator, whatever is on the below will go on the outside, and whatever is on the inside would be your numerator. Now you can always rewrite the expression as well as to be the root of a of x raised to the b. So those two are interchangeable. Sometimes it'll help you do one action versus the other a lot easier in some cases. Okay, so let's try it again, but in the opposite form. So notice you have an exponential and there's no logarithm in sight. So if you have the case b to the y is equal to x, to go into an x or a logarithm, we're still going to swoop. So starting on your base, coming up and around x and landing on y, very similar to the one before. Now, one thing that students end up getting wrong is to go from an exponential to a logarithm, you must write log to start. I'm even going to put that in a different color. You must write log, because otherwise what you've done is just made another exponential and it's not going to be an equivalent expression. So writing log is key. That's why I'm not a huge fan of the swoop method, is that because students kind of go too fast and forget about the log. So again, the order in which you're writing is the order in which you're swooping. So we have log base b here, and these bases must match. This is the base of the logarithm found right here, and your base of the exponential, the one with the exponent, is found right here. And then your next thing to write, we have x is equal to the last thing, y. So if we were to replicate that on the next expression, so we start on your base, locating your base, 81, swooping up and around and landing on 1/2. So again, we have to write log before we get started. Then we match your base, 81. I'm sorry for the little swishing in the back. We have 81 is equal to, or sorry, 81, and then 9 is equal to 1/2. Again, a true expression. All right, one more time. Starting on your base, up and around and landing on 2. We have log of 7. 49 is next, is equal to 2. Now, similar to the question before, or the series before it, I'm going to do a different method for this one. It's going to be kind of the reverse action of this. So instead of writing an exponential first, we're going to have perhaps log base b of x. So in order to get rid, so you'll notice here it's written a little bit differently. Oh, just kidding. I wrote the same exact thing. Silly me. So we have log b of b to the x. Okay, so this is what we're going to have on this sort of variation when you start with an exponential and need to go into the logarithmic form. So notice that if you have, again, these same bases and they match, but first having the logarithm and then the base, they're still going to cancel each other out and allow it to drop. So in this instance, think about from last time we said, okay, well, let's take the square first and then square root it. And then we also said, hey, we can actually write these either way. You can actually take the power first and then the root, or the root first and then the power is what we're going to do. So instead of writing the square root on the outside, we're going to put it on the inside squared. So they cancel each other out just like last time. Think about, let's say we take the square root of 4 squared. Well, the square root of 4 is 2. And then we decide to square it, we'll still get what we started with. We'll still get 4. So they're canceling each other out just like last time, but just in a different order. So for instance, where am I? Over here, number 6. Right? We want to match the base, but again, we want to write the logarithm. So we're going to be writing log, and locating your base, we're going to write your base, 16. What you do to one side, you have to do to the other. So we're going to write log, and not log of 256. We're going to write the same exact logarithm as the one before. The reason for that is that we get to cancel out the 16s and the logs, and your 2 gets to drop. 2 is equal to log of 16 to 56. Let's try it again. So we can write your log to start, and maybe you write it on both sides. And locating your base, we're going to write your base 12, and it allows us to cancel on one side and drop the 2. 2 is equal to log of base 12 of 144. Now we'll do a few more. Notice that this time we have a few more variables. Pick whatever method that you'll like the best, and then we can go from there. Okay, I'll still do the swoop. We're gonna swoop here. So we're writing x, y is equal to 191. And again, swooping here. Not x, 519 is equal to x. And in this case, you could simplify if you, not simplify, but you could, well, yeah, you could simplify if you wanted. That's just a lot of 5s to multiply together. So we're going to leave that one as is. We'll take a look at the answer key and see what they ended up doing. So this one, I'm going to just write the same base on either side. They cancel each other out. The n drops. So we have n is equal to 5 to the negative 2. Now we don't typically see negative exponents. So if we have a negative exponent, we end up changing its position. So for example, if we had some number times a to the negative first power, we're going to change the position of just a, just the value that has the negative exponent. So by changing the position, if it's located in the numerator, we're going to drop it down and put it into the denominator. So in our case, we just have 5 to the negative 2, their second power. So we're going to put it over a number, and even better, 5 to the 2, and we change it to a positive, and to just say, hey, without changing the problem, we're just going to have to put some placeholder number in there, which is a 1. Now, the reverse is true if you had some negative in the denominator. To change its position, let's put it right here. To change its position, again, we're just changing the value that has the negative exponent. So we're going to keep whatever is next to it down below, and we're just going to put it up top and make it positive. And one more time. We're writing the base this time in n, cancel. M is equal to n to the negative 6. So m is equal to 1 over n to the 6th power. And the reverse. So again, swoop, swoop. Don't forget to write log, the base, the next number, and then your exponent. Log, your base, the number, and the exponent. This one, we're going to write log of 19, which is your base, and do it to both sides, log of 19. It's going to cancel, and this 19 drops. So negative 19 is equal to log of 19x. Same thing here. We're going to write log of base b to both sides. They cancel, and your a value drops. And there you'll have it. The answer key should be attached. Notice that they did keep 5 to the 19 kind of restricted. You'll also notice that some of these, they did not simplify and get rid of that negative exponent. If you have me as an instructor, I will expect you guys to get rid of your negative exponent.